Are you interested in robots? Do you think that it can be useful in research based on operant conditioning? To answer the question, in this case, yes, it can be helpful to conduct a study on if robots can train humans using principles of operant conditioning through visual reinforcement tools. Those who conducted this research were Emily Kiezen, Charles Ira Abramson, and Christopher Crick. Lastly, Harshal Mask and Girish Chaudhry. The article Robots Can Train Humans Using Principles of Operant Conditioning Through Visual Reinforcement Tools is about how researchers have devised innovative methods to explore human-robot interactions, drawing on insights from interspecies communication and comparative psychology. Observations of animals accepting robot counterparts in intricate social settings have inspired the creation of robots that can adjust their behavior to both humans and animals. Using a robot equipped with adaptable algorithms designed by the researchers, they proposed that robots could employ operant conditioning principles to teach humans a simple task, utilizing familiar visual rewards as positive reinforcement. In this study, the robot autonomously optimized control of construction equipment by learning from the movements of an expert operator. It then attempted to transfer these skills to novice operators, using straightforward visual reinforcement techniques. This presentation is to show you the wonders of operant conditioning and how it can be paired with robots. The initial hypothesis was that robots could teach humans a complex task with basic operant conditioning by using green color indicators on a screen as a visual positive reinforcement indicator when the task had been performed correctly, and that this basic conditioning would result in greater learning than the more complex visual guidance interfaces used on the same screen. There were a total of 113 participants who volunteered for the study or were recruited through the University Research Participation System, also known as SONA. The average age of participants was 23.83 years, with approximately 72% males and 27% females and 26.5% Asians, 33.6% Caucasian, and the remainder of varying self-reported ethnic descent. All volunteers were active students, faculty, or visitors in the psychology and engineering departments at Oklahoma State University. The participants were evaluated by their actions. Participants' actions were assessed by analyzing the number of times the excavator bucket struck the truck, the average number of single movements required to position the excavator correctly, and the frequency of movement corrections. These metrics were quantified through video analysis and compared across groups to determine how closely participants' joystick movements resembled those of an expert. The procedure was started by randomly assigned participants to one of three groups to test the hypothesis that a basic graphical user interface, GUI, could be used for robots to teach human learners upon arrival. Group 1 consisted of 34 participants, Group 2, 41 participants, and Group 3, 38 participants. A research assistant introduced them to the GUI on the computer screen and explained the meaning of the interface. All participants sat in a standard office chair and viewed a guidance system on a standard 15 inches. Computer screens sat on a box slightly to their left so as to not block the view of the remote-controlled excavator located directly in front of them on the floor. Each participant has a minimum of 3 trials to attempt to scoop sand from the tub and deposit into the truck using the controls and the assistance of the selected training GUI. Participants were timed and videoed, and actions and times were then compared to ideals set in place by experts who had extensive experience and familiarity with the equipment. Participants then returned within 3 days to repeat the trial, but this time without any help of a GUI. Participants were divided into 3 groups, each using a different graphical user interface. GUI Group 1 used GUI circles, Group 2 used GUI speed bars, and Group 3 had no GUI. Each participant completed the task at least 3 times, with cycle times recorded and averaged for both the initial and retest phases. Various statistical analyses, including paired t-tests and ANOVA, were conducted to compare cycle times across groups and with the expert benchmark, 24.9 seconds. Extreme outliers were removed to ensure accuracy. Results indicated no significant differences between earlier trials. However, significant improvements were observed between retest 1 and retest 3 for groups 1, GUI circles, and 3, no GUI. ANOVA revealed notable differences in retest 3 times between groups, with Group 1 outperforming the other groups and coming closest to the expert time. The findings suggest that visual interfaces, particularly GUI circles, enhance performance, though all groups remained slower than the expert. Although the article is well written and provides valuable insights for those interested in the topic, there are several areas where it could be improved. For instance, while participants were randomly assigned to groups, the unequal group sizes, 34, 41, and 38 participants, could introduce variability that may affect the reliability of the results. Additionally, participants were given only 3 trials to practice using the GUI, which may not have been enough for them to fully adapt to the interface or demonstrate consistent improvement, particularly for those unfamiliar with the equipment. The study also required participants to return within 3 days for a follow-up trial without the GUI. This limited time frame may not have allowed for sufficient reflection or retention of learning, potentially impacting the study's validity.